Hi, I'm Professor Melko, Chemistry PhD, and your university chemistry professor. Today we're going to cover the concepts of mole and molar mass. And a mole is really just scientists' way to express a useful amount of atoms or molecules. So much like we buy a dozen eggs, because a dozen is a useful number of eggs, scientists use a mole, which is a useful number of atoms or molecules. Now, because atoms and molecules are so tiny, we need a really large number of them to do something useful with. So it turns out a mole is a really large number of atoms or molecules. So let's jump into the lecture. But first, a mole of coffee. Much better. All right, let's get started. So as I said, it's difficult really to count atoms individually, right? They're really small. So instead, as humans, we're really large by comparison. We need a lot of these atoms or molecules to do something useful with, right? So we count these groups of atoms, and that group that we're going to use is a mole. So much like you have these other units like cartons or dozens, right? You buy papers in reams, you buy cases of beverages, if you're old enough. That's just a useful amount of that thing, okay? Useful amounts to purchase at one time. So this concept of a mole that we're talking about today is really just scientists' useful amount of atoms or molecules. Now, this mole is abbreviated. The abbreviation doesn't really save you a lot of time, but it is 25% of the word, I suppose. You drop the E and mole becomes lowercase m-o-l, right? The word mole looks a lot like molecule, but they're vastly different, okay? 1 mole is 6.02 times 10 to the 23rd molecules, or atoms, or formula units, or baseballs. You can have a mole of anything, okay? So we can talk about a mole of any substance, atoms, molecules, softballs, etc. But this unit of mole is really at the heart of chemistry, okay? This number, 6.02 times 10 to the 23rd, was first hypothesized by Avogadro, an Italian chemist. And so now it bears his name. We call this Avogadro's number is 6.02 times 10 to the 23rd. That is the number of atoms in 1 mole of atoms. So the mole is so important that chemists celebrate it every year on October 23rd, 10 to the 23, at 6:02 p.m. in our local time zone. We all get together, nerd out about the mole, and celebrate with perhaps a couple moles of beverages. Now, it's hard to appreciate really how many atoms this is, okay? 6.02 times 10 to the 23rd, this is a really large number, right? You might operate in millions or billions for some things. That's 10 to the 6 or 10 to the 9. 10 to the 23 is much larger, okay? So if you imagine something like a mole of baseballs, that would fit in a container about the size of Earth, right? You would need a container that big, the size of Earth, to hold that many baseballs. Okay, so it's a really large number, right? Again, atoms are really tiny, so we need a lot of them to do something useful with at the human scale. Said another way, a mole of pennies could be distributed to all the current living people around the world, and they could spend $1 million an hour, every hour, day and night, rest of their lives, never run out of money, okay? That's how much a mole is. Now, in chemistry, we're often doing calculations to convert from one quantity to another. And we're going to use this concept of a mole as part of this conversion process. So if you haven't really mastered conversions, you can go back to my earlier videos on dimensional analysis, unit conversions, to learn how to do these conversions. All we're doing now is incorporating this notion of 1 mole is 6.02 times 10 to the 23rd as part of this sort of dimensional analysis. So I have an example here at the bottom of the screen. You might be asked for how many sodium atoms are in 0.24 moles of sodium, right? This is a useful amount of sodium to do some chemistry with. How many atoms does that correspond to, right? So we're wondering what atoms of sodium is. That goes on the right. The given information goes on the left. And in the middle here, we're using our unit factor. Because we're starting with moles of sodium goes on the bottom. Because we want atoms of sodium goes on the top. And the numbers that go with those units are related to one another by this concept of a mole. Avogadro's number of particles in 1 mole. So there's this many atoms in a single mole, right? So 6.02 times 10 to the 23rd goes on top. We multiply across the top. We divide by the 1 on the bottom, and we get 1.44 times 10 to the 23 atoms. A whole bunch of atoms of sodium to do something useful with. Let's try some more practice problems, Okay, you should try this one on your own. Pause the video here. I'm going to go ahead and work it out though. So imagine we have 2.50 times 10 to the 23rd molecules of iodine. So this is the given information. I'm going to go ahead and write it down on the left side of my paper. And don't take shortcuts, write everything out, especially because you might get confused between moles and molecules. So write out the whole words here, 2.50 times 10 to the 23rd molecules. How many moles of iodine do we have? So on the right here, I'm trying to get 2 moles of iodine given molecules of iodine. So what kind of unit factor do I need? I need a unit factor that expresses molecules of I2 and converts it to mole of I2, right? What do I use as this unit factor? This is the concept we just learned about. In 1 mole, there's 6.02 times 10 to the 23rd somethings. Here the somethings is molecules. Could be atoms, could be baseballs, doesn't matter. But this is the unit factor I'm going to use. So in 1 mole, there is 6.02 times 10 to the 23rd molecules. So now I take the given information, 2.5 times 10 to the 23rd, multiply by the 1, it's still 2.5 times 10 to the 23rd, divide by the denominator here, 6.02 times 10 to the 23rd, and I get, rounded to 3 sig figs, because that's the number I'm given, 3 sig figs, I get 0.415 moles of iodine. And you can always have this check in your head. You shouldn't get a astronomically high number of moles, right? You shouldn't get something that's like 6 times 10 to the 50 moles, right? You might have a large number of molecules, but you shouldn't usually have 10 to the 40, 10 to the 20 number of moles, right? So to make sure you're getting the units right, just have this conceptual check. You know, the number of moles is probably going to be a reasonable sized number. Let's try another one. Again, feel free to pause the video here and actually try to work this out yourself. Even if you fail, even if you have problems, trust me, you'll learn a lot more by trying yourself, putting pen to paper first, and then watching me do the problem. Let's solve this one. How many moles of potassium contain 1.25 times 10 to the 21st atoms of potassium? So moles of potassium, how many? So that's what I'm asked for. Moles of potassium. What I'm given, 1.25 times 10 to the 21 atoms of potassium. I want atoms of potassium to go away, so that unit goes on the bottom. I want to be left with moles of potassium, so moles of K goes on top. Now what numbers go in what place here? Mole is always going to be associated with 1. In 1 mole, there's 6.02 times 10 to the 23rd atoms. So similar to the last example, 1.25 times 10 to the 21, divide by that Avogadro's number. Round this to 3 sig figs, since that's what I'm given. 1.25 times 10 to the 21 divided by 6.02 times 10 to the 23rd atoms. I get 0.00208 moles of potassium, or 2.08 times 10 to the negative 3 moles of potassium. Correspond to 1.25 times 10 to the 21 atoms of potassium. Again, kind of a small number, but not something that's 10 to the negative 50 or 10 to the positive 30. Okay, so that's basic conversions using this concept of a mole. Remember, a mole is the unit. Avogadro's number is that actual number, 6.02 times 10 to the 23rd. Now, this unit of a mole we also use in relation to grams. So these atomic masses on the periodic table we've learned about before, listed in AMU or atomic mass units. right? That is cleverly chosen to correspond to 1 mole of that substance, okay? So although the periodic table lists these values, like for oxygen is 16, and we could write that as 16.00 AMU, in a more useful sense, that's been chosen to represent 16.00 grams of O2, or oxygen atoms, I should say, and 1 mole of oxygen atoms. So to say that another way, this 16.00 AMU is equivalent to 16.00 grams per mole, right? 16 grams and 1 mole. Okay, so this now might be our formula unit, or not formula unit, our unit factor we're using as part of conversions. Okay, but this is the atomic mass, right? This is expressing the amount of oxygen in grams that correspond to 1 mole of oxygen. Similarly, the number of carbon, or the amount of carbon atoms and mass in grams corresponding to 1 mole is 12.01 grams. So for 6.02 times 10 to the 23rd atoms of carbon, or 1 mole of carbon, there's 12.01 grams of carbon. So these masses are going to become important when we start doing conversions from grams to moles, or grams to atoms, or grams to molecules. Okay, so just recognize these periodic table values also have the units grams per mole, in addition to AMU, or atomic mass units. Now, molar mass is simply counting up these different atoms, multiplying them by their individual masses, and adding all those masses together. So an example is easier to see. Think about carbon monoxide. Okay, carbon here is 12.01 grams per mole. Oxygen, 16.00 grams per mole. Again, I'm just reading these numbers off the periodic table. If I want to know the mass of carbon monoxide, 1 carbon, 1 oxygen, well, 1 carbon in the molecule means I take 12.01 and add it to 1 oxygen, the atomic mass of oxygen. So I add these two numbers together to get 28.01 grams per mole. So individually, these are atomic masses, but for a molecule, I add those atomic masses up to get the molar mass. Just make sure here you're accounting for the number of atoms in the formula. Okay, because if this is instead CO2, well, now it's 1 carbon, 12.01, plus the first oxygen, 16.00, plus the second oxygen, because now my molecular formula tells me that there's 2 oxygens in carbon dioxide. So here I have to add all 3 of these numbers up now, and I should get 44.01 grams per mole. So that's the whole concept of molar mass. To identify the molar mass of anything, you worry about the number of atoms of each element, go to the periodic table, find those atomic masses, and then add them up corresponding to the number of atoms of each. Here for CO2, it'd be 44. Here for just CO, it's 28. Now you try. Try to calculate the molar mass of this more complex molecule, table sugar, sucrose, C12H22O11. Pause the video here, try to work it out yourself, and then go ahead and resume the video to see how I do it. Okay, carbon 12H22O11. So for something more complicated like this, I'll show you sort of the table that I lay out to calculate this. Carbon, hydrogen, oxygen. Okay, the number of carbons, 12. The number of hydrogens, 22. The number of oxygens, 11. The atomic mass goes in the next column. For carbon, it's 12.01. For hydrogen, I'm going to round this number to 1.01, just so everything is to the hundredths place. These are always grams per mole. for oxygen. So there was carbon, there was hydrogen, oxygen 16. And now I simply multiply left to right here. So the first row, 12 times 12.01. I get 144.12 grams per mole. The second one, 22 times 1.01, I get 22.22 grams per mole. Third one, 11 times 16, I get 176 grams per mole. Now I simply add up all of these to get my total molar mass. So 144.12 plus 22.22 plus 176, I get 342.34 grams per mole. So you can calculate the molar mass of anything this way, and it turns out moving forward in future videos, you're going to need this molar mass as part of more complex problems. So make sure you're taking the time to calculate these molar masses, and you can do it pretty efficiently on your scientific calculator so that when we get to stoichiometry and limiting reactant problems, you're able to calculate these molar masses pretty efficiently because that's really step one of the much more hard problems. So that'll do it for today's lecture. As always, if you like videos like this, feel free to subscribe to my channel on YouTube and check me out over on Twitch every week where we talk about the latest science news and answer whatever questions you have in chemistry. That's it for this lecture. See you next time.